All right, well, thanks you guys for joining it today. I'm going to go through a series of examples of utilizing what amounts to be kind of a global asset. And the asset is agricultural meteorology at 9-kilometer resolution across the planet, across the agricultural earth. The reason why I talk about it as an asset is we only scrape the surface, if you will, of its utility. We're focused principally in agriculture, but there's all kinds of adjacent efforts going on, everything from supply chain management of agricultural products to human health, and there's an example of that in here. So the first piece, this is something people trying to, if you will, warm up to why we are doing what we're doing. We know that right now there's some major issues going on with a combination of population growth and diet change, meaning different foodstuffs need to be produced. And also the atmospheric warming that we're experiencing has a very strong relationship with the increased variability that we're all experiencing. And agriculture is uniquely unsuitable, not suited for weather variability, partly because of the extreme events, which typically and easily cross some of what you might think of as an ecological threshold that is associated with any particular crop variety, species, however you want to refer to that. So the risk in agriculture is high, and we are seeing what we call pocket droughts. We're seeing a lot more of these extreme events. We're seeing, hailstorms, which have a very small spatial footprint, but can be devastating. And then, of course, we have what's happening in the tropics, where the rainy season itself is so disrupted, and I have an example of that just unfolded right now in southern Africa, that farmers need weather to be relatively normal because they have to plan for a certain sequence of events. So if the rains arrive early and stop, or the rains arrive late, that right there will reduce yields. And this is what we're experiencing. So this slide is just meant to say something really coherent about what aWhere does across the agricultural value chain. So some of these companies you'll recognize, like Monsanto or Microsoft. Some you won't. Some of these are quite small companies that are just getting going. The other point to make is not just about the size difference between some of our clients, but it's also where they sit on that agricultural value chain. So if you think of the value chain working your way, if you will, from left to right, on the left side, you have the far left, you have researchers. You have people who are literally trying to solve problems. And then you have like input providers, is a very simplified idea, where you're seed or crop protection or fertilizers. Then, of course, you have the producers. You have farmers of all sizes. And then to the right of that, you start to have the processors, those who buy this material that comes off the farm. And then you have even the commodity markets, and you go all the way as far as consumers who are obviously purchasing this. So for that simplified ag value chain, you start to realize that on this chart here of just a few of our customers, you have SGS, which is a very large organization in Europe, and they are primarily concerned with aflatoxins, for example, in maize, because they are the ones who are buying and storing and then reselling these grains. On the other hand, you also have the Monsantos and the Syngenas and Wilbur Ellis who are input providers, and of course you have groups then that send information to farmers, and then because of aWhere's particular history and what we do is we have a fair number of the development organizations like the World Bank or CTA, which is a Dutch organization, USAID. The point then is that all of this intelligence that we're talking about is based on a foundation ag meteorological data set, and that's what I'm going to touch on, which is a database. We construct a weather station's worth of data, and that's intentional, about every 9 kilometers, or for those of you who have a GIS background, 5 arc minutes, and that's across the agricultural earth. My point is there's a signal in the weather that all parts of the value chain need to have, and that signal needs to be coherent and what they call symmetrical. That's an insurance term. If you have to have symmetrical information, because the research scientist actually needs to know what the farmers are experiencing so that they can prioritize what they need to solve, if you will, as the new problems. One of the problems with a warmer, wetter earth is that a lot of the disease spectrums and insects emergence are coming at different times and showing up in different places. As an example, a few years ago I was in Kampala, and the front page of the paper talked about a 30% decline in common bean yields due to a foliar disease they'd never seen before. So not only did the farmers not know what it was, the input providers did not have a solution. And you can see right away what's starting to happen. These warmer, more humid nights were leading to things, foliar diseases, that they hadn't any experience with. And science is really the only way to go in some of these guys. So what aWhere has, this is our foundation information set. This is what we are making available to governments, to private companies, to NGOs across the planet. It starts over there on the left side. The base information is exactly what you would expect out of a weather station. That's the best way to think of that. Now, part of that is my PhD work. I actually was operationalizing the FAO soil water balance model. And the reason for that is it was the best they had in the late 80s, and this is a tool that worked because it was designed to take data off a weather station. So by doing this, what we're saying is just about any agricultural model, it didn't really matter where it is, if it uses weather, even a small amount, it's going to need something that looks like what comes off a weather station. So by replicating that, it's meant to be very much enabling and very agile. And so you have the variables you expect to come off that. We also offer some things like soils, and then there's a forecast. So this is all available through an API. And the idea here is that anywhere on Earth with an internet connection, you can pull data down for any location you wish. And you can also get forecasts. So you can get daily observed data up to yesterday, 7 days of hourly forecast updated every 6 hours. So this is the enablement. On the right-hand side are things that we do as a company. Now this requires a Hadoop cluster and some big data infrastructure, and we have 100 cores. We have what you have to do to be able to ask a question, which might seem on the surface very simple, but here's one for you. On the western slope, you have a certain sort of characteristic around your fruit growing, right? Where else on Earth do you have similar environment? Because that simple question would not only tell you what germplasm might be appropriate to that western slope environment, might also be, if you solve a big problem, where are farmers who would want to know the same information? Well, the only way you're going to find out all the places on Earth that are similar to that place is you have to characterize that place very accurately, and then you have to have those observations everywhere on Earth so you can go search for similar sequence of events. And we'll touch on that a little later. Excuse me. So this is our big data infrastructure outputs. These are the insights that we can do. The foliar disease one is what SGS actually uses. We are predicting conditions conducive, so they know to sample at a higher density corn coming off farmers' fields in parts of the Balkans that experienced conditions that were really conducive to the proliferation of various aflatoxins. Our story starts with the idea of actually helping farmers. This is where we kind of came from. And the idea is if you know something about what's going on at a particular farm and you have all of this information, you can start to provide all sorts of advisories, right? This makes perfect sense. This is what farmers do in information-rich areas like the U.S. where they look it up themselves. A lot of parts of the world don't have any information like this at all, and so SMS text messages become important. But when you start realizing that if you can do that from modeled environment, which of course you can, many of you have touched on these sorts of things, then if you can solve farmers' problems at that field, well, why not solve it for all the farmers in the area? Now, they all may plant different things at different times. It doesn't matter, right? This is the whole big data technologies. You take what you planted on what day you planted it, and you provide insight. But where it gets really interesting is the aggregate of all of those farms is a wholly different signal that can be leveraged by input providers who now know how much fertilizer to truck into this area, or the suppliers, the buyers, who need to know how much product is coming off. Therefore, you are optimizing the value chain by knowing all of these things. And this is a very real opportunity that is catching on quite a bit now. How do we do this? This is a very important part of our little story. On the left-hand side, you're looking at a map of Mexico. I think there's like, about 100 ground stations, and that's a classic GIS optimization of distance to the nearest ground station. So if you're pulling information from the nearest ground station, that's the kind of look that you're going to get for all of your output. And as you can literally tell, you compare that to the sort of spatial acuteness that you get on the right-hand side, and that's the difference right away. Because what we're providing with a surface is a very straightforward concept, and I think most of you are going to get this. It's a very easy idea. If you only have a couple of irregularly spaced observations, you cannot know what's happening in between them. Now, you can with temperature, but rainfall particularly you can't. But my point is, if you only have a couple of locations, the one question you cannot ask is how much, and you can go on with how many hectares, how many people for, say, famine, or how many kilos, how many tons of product are coming off. You just can't ask it. But if you have a surface, if you have a weather station every 9 kilometers or whatever, you can start to say, I know how many hectares are doing really well, and you can model the yield, and since you have the hectares, you can say this many tons. And the input providers can do the same math and say, we need this many liters of this crop protection because there's this much area experiencing these environmental characteristics. My point is, you get area, you get volume. And agriculture is a business that is fundamentally driven by volume. Whether it's the transportation costs of your inputs or the transportation costs of the product off the land, or you're a supply chain manager who can't buy it locally, you're going to try to figure out what's the nearest, most optimal place you can go buy something to fill your supply chain. And these sorts of surfaces begin the story to optimize the information stream across the value chain. So our data set is now north of about 1.7 million weather stations that are updated every day. These are virtual weather stations, okay? They're based on a whole bunch of ground stations and satellite data and some big data technology for interpolation of temperature and humidity, etc. We actually consume data here from Andy Jones's shop over at CIRA and CSU as part of the rainfall, because that's all coming off of satellites. We use the ground stations to calibrate those satellite estimates, but you build a daily weather station every 9 kilometers. Now, these next sets of slides are different things that we are intimately involved in. In fact, just this morning, talking to one of my colleagues, just got back from a meeting in Addis with Gates Foundation. They're pouring a lot of money into Ethiopia. This is the primary thing they're trying to do. They're trying to use science, best science, agronomic science, to give farmers a heads up to make what they do less likely to fail and thus less likely to need all of that food relief and other kinds of. This is very important stuff to a lot of the world. So we call part of our business Farmer Productivity Insight, which is data-driven agronomy. Now this, I guess this PowerPoint will be made available as well, so I'm going to jump past this to get right into the nitty-gritty. We all know that if you have a good forecast, you can make all kinds of decisions as a farmer. In fact, here in Colorado, if you have a forecast, you make all kinds of decisions about when and where you're going to drive someplace. And usually it's where you're not going to drive, right? You get snow in the mountains, it's like, I don't really want to go there today, okay? Why? Because it helps optimize your decisions. It makes sense. So providing the weather forecast is a fine thing to do, but it gets even more interesting when you start plugging it into all kinds of models. There's a big uptick right now, and I'll give the example of a sowing model. Literally, when should you sow? The monsoon in India has become so irregular that our data, working with Microsoft and ICRISAT, the International Center for Research in the Semi-Arid Tropics, which is based in Hyderabad in India, this little model, and all it did is it told peanut farmers when to plant, and usually it told them to delay, 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 and the farmers who believed it, somewhere between 30 and 50% yield increase, because the farmers that planted when they normally plant had this 3 and 4 week dry spell where the seed viability just declined, because there's all kinds of things in the tropics that damage seed. My point is, this is the sort of information set that you can start to realize is processed, and all of this can be done a fair bit automatically, right? If you know what the farmer planted, when they planted it, and where, there's all kinds of things that entire growing season can be tied to the environmental sequence of events that actually unfolds. You can give them better advice. So here's some examples. These are examples that we're actually involved with right now. FarmerLink, coconut disease prediction. This Recolt has actually just expanded out of Pakistan to Thailand, and this is just primarily a planting model. This is the Microsoft India one, and actually we just got word today with this livestock one is now a go, and even the herders want to know where it rained, because then the forage grasses will be better. And of course, in Kenya now they have a new government system, and they're trying to manage common lands better so that they don't degrade. All of this is an information needing set of decisions. So here's just some examples that were provided to us given the kind of impact, the kind of expected yield increases and things like that. The point here is sometimes, not sometimes, but the point is farmers given better information are going to make better decisions, and I think that makes common sense. So here's, I'm going to go through a sequence now of predictive modeling things that we do on our own cluster that are kind of massive, but it's a really interesting concept for here at Colorado State, where in a sense, a lot of the researchers here have some visions about these are the sorts of things that are important. So this first one, environmental trend, is really interesting. The World Bank is all over this because two of the main countries, Ghana and Cote d'Ivoire, they produce 60-something% of the Earth's cocoa. There's issues with cocoa, and the price of cocoa has actually gone up about 25 or 30% in the last 6 weeks because apparently it wasn't a drought. It was actually too much rain and too high of humidity at the wrong time, and the quality is really poor. But the point is, in this study, we were hired to look at the conditions. You characterize the variety of cocoa tree that they were talking about. You characterize what it wants, what it likes, what it thrives in, and what it really can't handle. Too dry, too long of this, too much humidity, too whatever. And you look at the last 10 or 12 years of data, we realized in Ghana, it's actually some of the cocoa areas there are degrading in terms of conditions that are optimal for this particular variety. And of course, what they wanted us to check was some areas they're starting to invest in Ecuador, and actually conditions are getting more conducive for that same variety. There's a story out of Brazil that I won't go into the details where they actually planted up in the northeast coast of Brazil. I want to say it's witches, it has the word witch, and it's a plant disease that affects cocoa. And unfortunately, all of the cocoa planted up there was susceptible to that one disease, and when it showed up, it really devastated that. And again, this point is as the conditions change, as the ambient conditions changes, so do the needs, and information can really help. Here's an example of site similarity. So there was a 20,000 hectare concession in southern Nigeria, and the question was, well, what can we grow here? What should we grow here? So we did a 10-day phase shift. We took the growing season in Nigeria, characterized it, and said, okay, let's look everywhere else on Earth that can find 160 days that look a lot like those 160 days of the growing season at this particular one in Nigeria, and you realize parts of Texas. So all of a sudden, you can go to India, you can go to Southeast Asia, and you can ask questions about what do farmers produce. Now, we're not saying that there's a market for that in Nigeria. We're merely saying they could grow it, things that are grown elsewhere. In this case, we're involved with a hybrid rice project, which has enormous yield advantage in East Africa. I mean, we're talking between 10 and 20 tons per hectare when the open pollinated varieties are often down in the 2 and 3. And at $500 a ton, that's a loose rule of thumb rule. That's a lot of money for a smallholder farmer. But the question is, where can you grow it? Here are the conditions that this hybrid rice seems to want. It wants this much heat, growing degree days. It wants rain like this, distributed through a growing season. So we can model that. We can tell you what is the first best 10-day period to plant it in. And all of a sudden, again, using information makes it more likely you're going to get adoption of a new technology. So any of you working on new things, whether it's a wheat variety or something in fruit trees, things like this can help you tell you where your market for adoption is likely to be better. This is an example from Recult. This is a sowing app. There's a lot of detail on this slide, which I'm going to kind of move too fast. But the point is, farmers need to know when to plant given the increase in the rainy season weather variability. Now here in Colorado, I was involved with some bean growers, common bean growers, and they're noticing the same thing. They don't know when to plant exactly because they want to plant early, but they also know there's a higher incidence of freeze. There's a higher incidence of hailstorms, which damage the. But if they plant late, they can get too hot and dry. And so when to plant becomes kind of a guessing game. And using big data technology can sort of skew that to your favor, right? Gives you better odds of making the right decision. And here's the example from SGS where we're modeling conditions conducive to various foliar diseases, in this case aspergillus, and telling them where they need to sample things a little more diligently. Because we have a weather station's worth of data, we can calculate potential evapotranspiration. This is right out of the sort of FAO from Drainage and Irrigation paper 33, 56, 66. I mean, these are details of the ambient environment that then tell you how much water the plant's going to need, which obviously translates to an irrigation need. And so we do a lot of, we provide PET and other variables to irrigation companies that calculate the hydrobio. Was a customer as a small emerging company, and they were bought by Monsanto this past summer. Now, on the food security side, here we talk about using exactly the same kind of a construct around whether you're tracking sugar cane or coffee or cocoa for commodities. Now we're talking about food. And what's interesting here is it's really hard from a satellite to determine what crops are planted in an intercrop situation. So sometimes there's an overemphasis on the use of satellite for food, but there's a growing sense that actually some of the models that have come out of the agricultural sciences can actually provide even more early warning, because turning green takes a couple of weeks, and if you already know that it rained, you can already start optimizing what will then happen. So there's some interesting things here. So here's what unfolded this last couple of months in southern Africa. So what you're looking at is a map here of Zambia, Zimbabwe, northern Mozambique, and Malawi. And this was a map. This is updated every day. This is a sequence of things that aWhere produces on top of those daily data. So every day we do a -7, -30 day look. It's collapsing the weather information into ag meteorological information into some information, some aggregate information, signals like moisture stress, P over PET. We also provide a forecast so you can see the two. So this is looking at the last 30 days, and I pulled this out on January 22nd. And the map is then the difference between this year, the current, and the last 10-year average. And as you can kind of see from the chart here, we're talking -2 or 300 millimeters of rainfall they did not get. And this little crop calendar here from FAO is showing that mostly they plant in November, December. So this is literally day anywhere from day sort of 35, 38, day 15. And this is a rough time to not get any water if you've planted maize. And by the way, they're expecting several hundred millimeters. So this is not a poorly watered area. This is a well-watered area. Drilling in a little more with that same map. Now, this is just using R. And this is using R and hitting our API and pulling the data from early October, and you're taking a look at different things, and you can see the failure of the rains, where it rained up till about January, wetter than normal, and then just went 0. Then as you get further south, you can see that, in fact, less than 100 millimeters of rainfall is not going to produce anything down there when they were expecting upwards of 350 to 400. All right? You can run various rolling forward, various charts. This is all done now using R. The map is made using QGIS. Obviously, you can use ArcInfo. You can use these different tools. You can use Python. The point is, these are open source tools, QGIS and R. And you're able to do an enormous amount of analytics. And of course, these sorts of charts can be literally produced anywhere. Every 9 kilometers, you have different data. Drilling in even further. So previous slide, I don't have it on this one, sorry. Previous slide. So this is southern Malawi. Okay, and all I've done is drill into and mapped the January rainfall. This histogram is then exactly the count of locations for how much rain fell in January. And look at how incredibly striking this is. This very simple visual is simply saying, this is what happened. This is what you're seeing this year. This is 2017 or 2018 January. This is what they expected. All right. This is using real-time information. You can update this sort of thing every day. You can customize it, you can drill in, you can do all kinds of things. And this was some headlines that I took off the newspapers, online, starting February and March. Meaning our data were right on. We're not missing a signal here, guys. But what's really important is you can't do much for farmers who aren't getting any rain. But those farmers in northern Malawi, which I didn't show, actually got enough rain. They didn't get anywhere near average, but they got enough. They should have got the signal to double down on fertilizers so they could produce more food, because the country as a whole is going to come up very short. All right? And so will Zimbabwe and some of the areas that counted on this for their supply chain, because now I think one of these articles says they're going to stop exporting. And you can see where I'm headed here. This information, symmetrical information, means everybody gets the same signal. You can make better decisions. Now, this example takes that one step further. So we're involved with a rather large 6-year project that's getting going in Mozambique, and it has both agriculture and forestry. So this is actually a forest reserve. And all I did was go into QGIS and grab the grid cells that cover that forest reserve. This is what it looks like. And then we did a very simple soil water balance model. So we pulled the soil data from every one of the grid cell locations. We looked at the actual distribution then of when it rained and how much it rained. And we're looking at a map here showing the evapotranspiration deficit. And this distance is only 72 kilometers. And they're going from just under a 100 millimeter deficit to well over or almost 300 millimeters. And as you can imagine, the forest in this area is going to be suffering pretty badly here. And then from another slide looking at, I don't have it here, a year before, they also had a drought in that area, whereas the rest of Mozambique was doing well. So this forest is suffering because they get one rainy season a year. The human health story is I'm going to go quickly here. This is just predicting malaria. And it's a one-to-one relationship. When it rains, Anopheles mosquitoes' eggs, the mosquitoes emerge according to temperature. If people are carrying the malaria parasite in their bloodstream, a mosquito bites one person, it takes a few days, and it takes a little longer for that to get from the gut to the salivary glands, and the next person they bite, they can infect, and that's called local transmission. As temperatures rise in Ethiopia, they're getting outbreaks of mosquitoes, outbreaks of Anopheles that are able to carry this parasite to populations that have very little immune because they didn't grow up with it. And as you can imagine, it has enormous economic repercussions when you have an immunologically naive population getting sick. So the moms and dads are getting sick now, not just the kids. And that's pretty bad. And these are just some charts showing how much the rainfall predicted the local, this is actually the blood samples that he's using from the local clinics. So winding up here, and then we were going to just take some questions if you like, but this was put out by one of these companies that tracks a lot of small emerging entrepreneurial efforts, and it's interesting to see all of the companies from sensors, robotics, marketplaces, precision agriculture, predictive analytics is where they put aWhere. And the idea is enormous amounts of technology, as all of you are aware, pouring into agriculture. There's a lot of aggregation rolling up. I mentioned how Monsanto bought one of our clients, HydroBio. This is happening more and more. The point is technology is becoming, and is, well, it's been that way for a while, but the information technologies are providing farmers and the value chain better and better ways to optimize their decisions, meaning they become more profitable, but they also become more productive. And that same need is actually really high across smallholders, South Asia, Central America, and Africa. And slowly, those sorts of technologies are making their way, sifting, if you will, the most important ones first. It's a very interesting place to be working. And with that, I'll kind of wrap up the formal presentation, and thank you all for your time and attention today. So I think we can, I don't know if there's any questions from you guys, but I'm happy to take some questions, and then, yeah.
To access the data for a specific location, so like we have 23 different field trial locations, am I able to put in like a GPS coordinates?
Yep.
And it just pops up?
No, it doesn't just pop up. Are you going to use R, for example, or Python? Yeah, if you go to aWhere.developer.com, we'll give you, I want to say 2 weeks, but it might even be 30 days of access to the last 18 months of data. And there's a bunch of things you can just download and install in R. And yeah, I'm learning R. I'm getting actually better at the tools that I want to use, but absolutely, you can use latitude, longitude, and just pull the data you want right out. And if you have some familiarity with R, you'll understand it. People who know R can do that, so that's easy.
And we can pull not only like that sort of standard weather data,
Mm-hmm.
but one of the things I was thinking about is your soil. I don't know what I'm really talking about entirely, but
It's fine.
we're interested in learning the variation of where all the climatic variation of where our plots are,
Mm-hmm.
and then ultimately using that information to sort of predict how different varieties would do in different areas is the idea.
Mm-hmm.
But so we'd be able to pull some of the, I mean, you can pull soil data from that.
No, in particular, this is U.S. based, right?
Yes.
Yeah, no, you would be better off going to NRCS, because then they have the Sergo online. And so you can pull the Sergo data, which would be better data. That would be the best available in the U.S. So the data that we provide, we tend to provide it for areas where you don't have any other option, and we use the ISRIC stuff. And these are publicly, I mean, these are available data sets. We just help make it easier to get to. But I think what you're trying to do is exactly the kinds of questions we need to start asking, which is what should grow better where, and that's very important.
We've just been, and again, so I work for the breeding program, I talked to you before, and we're just having a hard time finding data that is, A, close enough to where our locations are,
Yep.
and that doesn't just have giant gaps
So-
over time, and so trying to find a thing where it all kind of comes together would be the most useful.
I'd be happy to work with you. So our claim is that we have 100%. We don't. We have found some interesting little odd missing bits now and then, but we're backfilling. We're making sure. Maybe we're already at 99%. I mean, it's not that big a deal. But what I would suggest is that interpolating temperature and humidity works very accurately. These are three-dimensional curvilinear functions, and they work because they adjust for elevation. Rainfall, you have to use a satellite-based system because you can't interpolate rainfall. And we can go into the whole rainfall discussion because where you're working, you could put rain gauges every 2 kilometers, and they won't agree with each other. So these are good data. They carry the agricultural signal. They'll get the difference. They may be off by a bunch in a wet year, and they may be just about right in the medium years, and they will be exactly right when it never rains. I mean, it's that weird thing that says the years where you need it the most is actually when I think our data differentiates itself the most. We tend to underestimate large rainfall events because satellites just don't quite do that yet. Well, that's kind of my point, isn't it? So But the point is that we will tell you, I will tell you, we have 100% of the data every day. And you're never more than about 6 kilometers from one of our centroids, if you will. And so that's a good way to start.
And I think that that's the biggest issue for us has been the variability, not just between our locations, but from years. We just don't, we haven't, we end up having to release sort of varieties that do well across everything.
Mhm.
Because we can't predict even
Right.
remotely close if Burlington's going to look this year like it did the last 5 years.
Yeah.
So we're kind of getting more, I guess, collections of ideas of what those actually did look like and what the variables were over time.
Well, see, and I think from now, I mean, we're applied scientists, right? That's what we do. If this research project had some room for us to do some of our environmental trend over your areas, we could start to provide you guys with a very interesting signal of that variability that your particular crops and varieties and cultivars are sensitive to, because that's exactly what it's designed to do. But, I mean, we can talk about that. But, I mean, from my perspective, like that map from Malawi, that level map is available anywhere on Earth, right? You can zoom into this part of Colorado. You can do these things, and it's just a question of working with us. That's what we do. And that's the asset we're bringing to the table. Any other questions?
Some people may not know how far back you go.
Oh, I like to use data only from 2008, but we do go back to 2006. I just know that Andy's data came online about 2008-9, and I like having that little extra CSU bit. It's not complete coverage, but it augments the, quote, complete coverages. And that rainfall information is getting better and better. I mean, obviously, the observed data go further back, and we can go back into the 70s, for example, for some of the temperature information. But at some point, I also want to caution you. The atmosphere warming has actually changed. And I've had some really interesting conversations. Because of our information set, I had an opportunity to talk to an atmospheric physicist from the Max Planck Institute. Very interesting guy. He was really friendly, but I was kind of intimidated, as you can imagine. But he said a couple things that I just want to convey. So we basically say the Earth is warmed up about 1 degree C, right? I mean, it's a little less, but it's about 1 degree C. His whole point was, he said, you know, but John, the problem is there are nonlinearities in the power equation. And what he was referring to is the amount of energy in the atmosphere to do work, which is the weather, is nonlinear. And the best way he said to explain it is, let's say that this 1 degree it warmed up about linearly over the last 120 years. So you have 40 years, 40 years, 40 years, about the same, right? But the power is nonlinear. So the first 40 years, not much changed. Second 40 years, you started seeing some odd things, you know, but the last 40 years, all of a sudden, this wild swings and droughts and rains, and look at how wet we are in the spring here in Denver. I mean, this is what, third year in a row now that we're getting this, we're being saved. Our snowpack is in the 60s and 70%, and all of a sudden it's going to be, if this keeps up, it'll catch up. My point is there's so much we don't even understand about how the weather, localized in particular, is going to impact. And what we do is we track the weather very closely. But my whole point in going off on that little tangent is to say, I don't think you really want to use data older than about 2005 anyways, because the signal that's in that data is for a much calmer kind of environment than what you're getting today, if that makes sense statistically, right? The variability today is so dramatically different. If you include those older data, you're actually dampening the very signal that you need to know more about. So that's my 2 cents worth on that particular story, which is why insurance companies, by the way, I think are really struggling, because they're grossly overexposed because they keep wanting to use 30 years worth of data for their statistics. They're just introducing signal that is the wrong signal given the risk they actually have.
Can you talk about briefly just you working with the World Bank now?
Yeah, that's actually really exciting right now. I mean, it's 2 weeks ago they flew 3 of us out there to present to the Ag Forum, which is the 350 or so World Bank employees who work in their agricultural practice. And I think presenting something kind of similar to this, talking about the surfaces, it's this idea that agriculture is all about volume. I mean, if you're in Mozambique, if you're in Angola, it's how many tons of fertilizer can you distribute to the farmers? I mean, they're trying to help them. So we help them say, well, those farmers are the ones that need it this year, and these guys over here are too dry, so don't. And that right there is something they can't see from a few weather stations. As you can see, what I'm getting to now is there's a lot of interest in the kinds of questions that you can ask of a system like this. I think it's quite interesting that none of you have asked how accurate it is, because it's pretty good. I mean, it's just that often is the first. But once you get past that, I think one of our more interesting discussions went on like this. One of the bank loans is about $30 million going to a country, and honestly, I don't even remember which country it was, but it was to buy weather stations and install them. And she was asking me, and actually our primary contact in the bank, Eric Fernandez, runs the World Bank's Agricultural Observatory. And Eric was saying to her the same thing that I now am saying. You need more users of ag meteorological information. You don't need more ag information yet. In other words, rather than buying $30 million worth of weather stations, why don't you buy $2 million worth of weather stations and spend $28 million getting more people to use the information to make better decisions, because then they'll demand better data and you can justify it. But if you just buy more weather stations, you're stuck in this funny loop where you don't yet have enough users, which is the reason why I'm here at CSU. My encouragement is, let's work together. Let's get student projects working together. And yes, of course, it requires a subscription to what we're doing, but we can talk about that from a totally different perspective than if you had enough users. And to me, that's what this R is causing to happen. We actually do capacity building. We show people, we give them scripts, because then they're running models that they design that fit their issues, because there's no way we could possibly do that for every country. So it's kind of it's a big thing happening now, the World Bank. So. Okay, so I'm going to answer that, or I'll address that. Okay, our forecast is GFS. We just make it easy to get to. So it goes out 7 days. You can get 15 days, but as you all know, those next 7 days are not that great. But agriculture does some different things, right? If you already know that the crop has done well for the first 45 days and the soil moisture is pretty good, you can predict pretty accurately harvest 45, 60 days out. The weather becomes really important if you're marginal, but less so if you're good, and obviously if it's horrible, it doesn't make any difference. My point is, prediction can be a lot of different things in agriculture, weather being just one of them.
Well, I mean, maybe, and I think not necessarily like predict that kind of a prediction, but if the analyzing sort of the trends using the data.
Okay, and that was the other piece.
What I'm trying to look at would be, based off of the data that you guys have, can we look ahead and see where we are in a trend a bit to try to and I'm looking at it from obviously variety choice.
I would say absolutely.
So something like that.
Absolutely, because that's actually what we're doing with that cocoa piece. We're literally saying to the breeders, guys, this is the new conditions. They need to handle a longer dry season. And the breeders are, okay, I got that, and they're working on it. It's like coffee. Coffee has a huge amount of breeding effort going into it for not only disease resistance, but for some of these other abiotic stresses which are showing up. But I think I would like to learn more about that, because that's where we sit. But I think this environmental trend piece is, to me, is one of the real opportunities of using our Hadoop cluster. I mean, we've already built everything you need to do that analytics. You just characterize what you're after, take the area you're interested in, and we'll show you which way it's trending. And that right there can be a lot of signal. That's important. And it's using big data, quantified metrics to say, we think it's going to get more like this in the future.
Which then for us, what we are doing is actually predicting, looking at patterns in the genome and predicting performance, incorporating the environmental variables so that then we are essentially breeding for that very thing.
Yeah.
But we just don't know what to put into the prediction.
Let's talk, because I think we might give you at least some interesting things to consider, just given the recent past and the fact that things are changing. Now, whether they're changing to a point where they're actually predictable, we'll see. But again, we're using some good applied science to help people who actually have decisions they have to make, and that's kind of the space I sit in. So. Hey, well, thank you very much, you guys, for taking the time out on this rainy day to come to this thing.
Thank you, John.
Yep.
Thank